Now, like we discussed in the previous video, based on the Boussinesa equation, you can have three different pressure intensity distribution. Number one being the isobar. So isobar is nothing but an imaginary line beneath the ground level which joins points of equal stress intensity. The pressure bulb was one such example, which corresponds to 0.1 or 10% of the applied load. Now the other two distribution diagrams are the vertical stress distribution diagram on a vertical plane, which means you have the ground level here and you have a point load Q applied at this point, and the equations which govern the distribution are this, right? IB into Q by Z square, where IB is given by Boussinesa. Now on a vertical plane, which is at a distance r away from the axis of Q, if I draw a line there, the vertical stress distribution on that vertical plane would look like this. So it starts at 0, it has got a crescendo there, and it starts to reduce once it goes deeper and deeper. So that's a distribution on a vertical plane. Now likewise, you can have a vertical stress distribution on a horizontal plane as well, which means I can draw a horizontal plane there marked in dotted line. So I can have the same vertical distribution on a horizontal plane. So it looks like this, quite similar to the bell-shaped curve there, with the maximum value of the crest just beneath the load Q. So these are two different stress distribution or pressure distribution diagrams other than an isobar. Now you can find detailed descriptions on these stress intensity distributions if you refer to any standard text. Due to the time limitations that we have during the class hours, I thought I'll limit to this one single slide. We'll try to move into a few numerical problems based on whatever little we have dealt with in the theory portion. The first question: you have a concentrated load of 2 kN applied on the ground level, and you're asked to determine the vertical stress at a point 6 meters directly below the load, which means it's something related to a point load, right? You have the ground level there and you have the point load, which is 2 kN, and the point of our interest is 6 meters below the point of application on the ground level, and since it's directly below the load, radius r turns out to be 0, right? So clearly it's a numerical problem which demands Boussinesa equation. It's something related to a point load. So you can adopt this equation: sigma zp is equal to ib into q by z square, where ib is 3 by 2 pi 1 over 1 plus r by z square raised to 5 by 2. So in this case, you are given with three values: q is equal to 2 kN, z is equal to 6 meters, r is equal to 0 meters. So substitute that in equation. In this equation I have substituted r equal to 0 and z equal to 6, and you substitute the value thus obtained of ib into this equation, where q is 2 kN, right? So substituting these three values into the equations that we know, you'll get ib into 2 by 6 square, which turns out to be of value of 0.0265 kilopascal approximately. So this is the simplest question that you can expect from the Boussinesa equation. Next question, it's quite similar. You have the same case. You're asked to find the vertical stress intensity at a point same 6 meters below the ground level, but the radius is not 0. Instead, the target point is 5 meters away from its axis, which means you have the same thing. You have the ground level there, you have the 2 kN load Q there 6 meters below, and 5 meters away you have the point P. So in short, you have capital Q equal to 2 kN, Z equal to 6 meters, and R equal to 5 meters. So you go for the same equation, sigma Zp, IB into Q by Z square, where the new values when substituted gives you IB into 2 by 6 square. IB gets modified here since you have a different R other than 0. So that's the only difference that you can have here, and sigma ZP value turns out to be 0.071 kilopascal. It's quite simple, but the takeaway from these two questions is that compared to the previous question, you have an increased value of R. So once the value of R increased, sigma ZP decreased, which means as you go radially outward from the axis of the point load, the stress intensity starts to decrease. Next question, you have to calculate the vertical stress intensity at a point P at a depth 2.5 meter directly below the center of a circular area of 2 meter radius subjected to a load of 100 kPa. So you have 100 kPa load stress applied over a circular area of 2 meter radius, and you're asked to find the vertical stress intensity at a point P, which is 2.5 meter below the point of application of the stress. So clearly it's something related to circular area, and you need to go for IC into Q equation, where IC is equal to 1 minus 1 by 1 plus radius by z square raised to 3 by 2, where radius is 2 here and z is 2.5. So once you substitute that, you get the value of IC, and Q is nothing but 100 kilopascal, already given the question. So sigma ZP IC into Q is equal to IC into 100, which gets a value of 52.4 kilopascal. Again, it's just a direct and simple application of stress intensity beneath a circular area. Next question, you have a wall of a building foundation which is 3 meter wide and it carries 300 kilopascals of UDL on 30 meter length. So you're asked to compute the vertical stress along the center of the foundation 3 meter below it, which means it's something related to a strip foundation. Probably most of your homes will be on a strip foundation. If your house is just 2 stories or perhaps 1 story, it can be expected to have the strip footing. Now in that strip footing, if you have 3 meter width and 30 meter length and it carries 300 kilopascal, you're asked to compute the vertical stress at the center point 3 meter below it, which means I can show this picture and it might perhaps give you a better understanding. This is the width of the strip, which is 3 meters, and Q, the load intensity, is 300 kilopascals, and you're asked to find the stress intensity at point P, which is at 3 meter depth below the ground level. Now again, clearly it's something related to not point load, not circular area, not rectangular area, but a strip load, right? So you go for this equation, Q by pi into 2 theta plus sine 2 theta. Now from this picture, if you want to get theta, one tip that you have is that you know opposite side and you know adjacent side. So you can go for tan theta is equal to 1.5, which is half the breadth, divided by 3. So tan theta is equal to half, which gives you theta as 26.56 degrees. And Q is already given in the question as 300 kPa. So you apply those values into the equation, 300 by pi into 0.926 plus 0.79. 2 theta in radians and sine 2 theta with 2 theta in degrees. When applied gives you 0.79. And on solving this equation, you get the value of sigma ZP roughly as 165 kilopascal.